So today we're going to go ahead and talk about Newton's law of gravitational forces in more detail. So the cool thing is lots of us, or many things in this universe have this mass, and we all have some gravitational attraction to each other and all the objects in the universe. The crazy thing is it doesn't always seem like it because we are pretty, I'm not going to all of a sudden be pulled across my room to my couch without me physically doing it. And that's just because oftentimes in our everyday life we're dealing with some small forces, but there are a lot of big gravitational forces that we deal with in our lives, like the Earth. I am so gravitationally attracted to the Earth. When I jump up, the Earth pulls me back down. Wow, so cool. So when I think about it, there's a big equation that governs all this. So if we have an object of mass m, let's call it m1, and we have another object of mass 2, okay? So mass 1 and mass 2 are the masses. We will oftentimes put those masses in kilograms. And then the distance between these masses, center to center, is going to be r. So r equals the distance from the centers of two objects that we are finding the gravitational force from. So again, it is center to center distance. Oftentimes people call it like the radius, which I know is confusing because it's not really a radius exactly in this case. But again, that is r, the radius. And oftentimes we will want that measured in meters. Cool. So the equation governs is going to be Fg, so that is the gravitational force. So M1 and M2 exert an attractive force on each other. It's going to be big G, which I'll explain what that is in a second. That's a constant, times M1 times M2, all divided by radius squared. Cool. So G is going to be the universal gravitational, and the number for this universal gravitational constant is 6.67 times 10 to the negative 11. And this is the same everywhere in the universe. So no matter where you go, G is always that same number. While little g, acceleration due to gravity, we know on the surface of Earth is about 9.8 meters per second squared, while on the moon, little g is 1.6 meters per second squared. Little g varies. Big G, universal gravitational constant, is the same thing everywhere. Wow, that is so cool. Let's think about what the units are for G. So what I want you to do, go ahead and look at this big equation, guess yourself what the units are for G, and then we can check back in. Okay, so now we'll go ahead and do it together. So let's solve, again, we're solving for the units for big G. So big gravitational force is measured in newtons. We want to find the units for G. M1 we'll want in kilograms, M2 in kilograms, R meters. So let's go ahead and do some math. So multiply both sides by meter squared, and then I can divide both sides by kilogram squared, and that will give us G. So the units for G are going to be Newton meter squared over kilogram squared. Cool. That's so fun to find the units ourselves. And again, Fg is, again, the gravitational force, or gravitational attraction between two objects. And I want you to think about to yourself, does it make sense we're dividing by r squared? Okay, so I think to myself, if M1 and M2 get farther away, is there going to be more or less attraction? Less attraction. So it makes sense that we're dividing. Like if you have a bigger distance between the two objects, R will increase, which will make Fg decrease. So cool. Physics works out. Love it. Cool. We're going to go ahead and look at a table together and then two example problems. So what I want you to do first is imagine we have the Sun, and we have Saturn, and we have Earth, and we have Earth's moon. What I want you to do is go ahead and just draw a little picture showing what orbits around what. Pause this video and then check back in. Okay, so after you've done it so we know this good old Sun is the center of the universe. So let's draw our Sun there. So what is closest to the Sun? Yeah, we know Earth is closest to the Sun, and Earth orbits around the Sun. And then Saturn, oh my goodness, that's going to be way farther out. Let's go draw our friend Saturn way farther out, and it is also orbiting around the Sun. Okay, Earth's moon. So that orbits around the Earth. So let's draw that in different colors. So here's the moon, and that is orbiting around the Earth. Okay, so a couple things to think about. So planets, this is not true. Realistically, planets move in elliptical orbits. Elliptical, so again, that's like an oval shape around the sun. It is oftentimes true. We will approximate this, and they are approximately circular orbits as something orbits around the sun. So the Earth orbiting around the sun is approximately circular orbits, and this table is just kind of approximating that. So, yeah. So again, like this table has like an orbit radius, which is the average distance from the sun or the planet. So let's talk about a couple things now in this table. So what I want you to think about is what is the radius, what is the orbit radius, and what is the period? And then check back into the video. So after you've thought, let's go ahead and think about it together. So let's see, let's look at Saturn because we have that on our table. So Saturn has a mass. So we know the mass of Saturn is 5.68 times 10 to the 26. Okay, got that. The radius is 6.03 times 10 to the 7th. So that is just the radius of Saturn. So that is like that little distance right there is going to be 6.03 times 10 to the 7th meters. Well, Saturn also has an orbit radius. So I want you to think about what that is. That is the distance or the average distance from Saturn to the sun. So this is going to be called our orbit or the orbit radius. And in this case for Saturn, so it's the distance from, and keep this in mind, it's the distance from the center of Saturn to the center of the sun. And in general, the definition for orbit radius is it is the distance from the center of that object to the center of the object it is orbiting around. Again, it's always the center to center distance. So that radius right there includes the radius of the sun and includes the radius of Saturn. Cool. So this orbit radius right here, so we have sun and Saturn. So this is going to be, what is this? It is 1.43. So in this case, it's 1.43 times 10 to the 12th. Cool. That makes sense looking at our picture. This is 10 to the 12th for the orbit radius, while radius of Saturn is a lot smaller than that. Cool. We could look, so now we have for Saturn, let's also look at the period. So the period's 29.45 years. So that means it takes 29.45 years. Oh, wow, I didn't even draw it on the orbit. I already drawn. It takes 29.45 years to go once around the sun. So it takes a long time for Saturn to go around the sun. Cool though. Cool. So what I want you to think about now, one interesting thing I observe about the table, why is there no orbit radius for the sun or orbit period for the sun? Think about that yourself, and then we'll talk about it in class someday. Cool. So we have one more problem we're going to talk about. What I encourage you to do, go ahead and draw this out, try it yourself, and then check back in on the video. Okay, so first thing we do after you tried it yourself, again, we always draw a picture. So I'm going to go ahead and draw our friend Pluto. So we have Pluto, and you are 3 million meters above the surface of Pluto. Okay, so I'm going to draw someone all the way out there. So 3 million, that's what, a 3 and 6 zeros. And you're in a huge spaceship. Okay, let's see if I can draw a spaceship. I'm not very good at spaceships. Okay, let's say that's a spaceship. The combined mass of the spaceship and you is 2,400 kilograms. Okay, we want, and again, let's say the spaceship itself has like negligible radius. That this 3,000 meters is the distance from the surface of Pluto to the spaceship. Okay, now we want the gravitational force between you and Pluto. Cool. So go ahead, and let's, you know what? Before we do that, let's go ahead and go to our table and write down some more distances, just so we can get it ready. So we might, just because we might, need the mass of Pluto. Let's go ahead and look at our table and see what that is. And I have for the mass of Pluto for my table 1.31 times 10 to the 22nd kilograms. And again, this is in the video if you just scroll back 30 seconds or so. Okay, now let's look, just so I have it, I'm going to write down the radius of Pluto. Just because I drew Pluto, it's going to be nice to know the radius. So the radius of Pluto is 1.15 times 10 to the 6 meters. And again, I didn't draw the orbit radius of Pluto on, which the orbit radius is bigger, 5.91 times, oh, no. 5.91 times 10 to the 12th meters. I didn't put that one on there just because we're not talking about the sun. We're just talking about Pluto on the spaceship. Cool. So now let's go ahead and write down our equation. So we have our gravitational force is going to be big G times the masses of the two things we're looking at. So we're looking at mass of Pluto and mass of, what is this? Spaceship. So we have those two things we're looking at divided by the distance between them squared. Again, it is the center to center distance. So now let's think about what numbers to plug in. Okay, you try it yourself and then check back in. So G I know is 6.67, 10 to the negative 11. Mass of Pluto, we already have that, and it's in kilograms. Love that. 10 to the 22nd kilograms. Spaceship, 24,000. Oh my goodness, if I can get this to actually work. Darn it. Got the pen to work. Goody. Okay, so again, the mass of the spaceship. Oh my goodness, if I can actually get this to work. Okay, cool. Now we're good. Mass of spaceship is 2,400 kilograms. The radius or the distance between them. Okay, so let's look at our picture again. We need the center to center distance, which is going to be this whole thing. I want you to think about, what do we do to find the total? Oh, cool. The total is going to be the sum of those. So it's what? 1.15 times 10 to the 6 plus 3 million. Oh my goodness. Big old number. And that's essentially like 3 times 10 to the 6, which I believe that is 4.15 times 10 to the 6. Cool. So now we can plug that in. Squared. Cool. And when I plug that into my calculator, I'm getting 1,217 newtons. And again, we might get slightly different because of units. One little thing, make sure when you're plugging things in the calculator, you have parentheses around the whole darn thing. It's so easy to make a silly mistake when you do that. So make sure you have parentheses around each thing. It just makes your life a lot easier and it helps avoid silly mistakes. Cool, we have one last problem to do and then we'll be out of here. Okay, so we're going to do this problem that I call 44. I got it from somewhere. It's a great problem. Great. Okay, so let's look at it. So we have two large objects. Again, try it yourself and then check back into the video. So two large objects of equal mass, so I'm going to call it mass M and mass M, separated by a distance r and exert a gravitational pull. Okay, I'll just go ahead and write down what gravitational pull they would exert. So again, that's our gravitational force equation. So G mass times mass over r squared. And Fg could be a number. We're just going to call it Fc. So now, if the distance between the two objects is reduced to r over 4, so now we're going to go ahead and draw them closer. So now it is r over 4, the center to center distance. What is the new gravitational force acting on each object? So what I want you to think for a question multiple choice like this, first take a guess. So if they're closer, is there going to be a stronger pull or a weaker pull? Yeah, if you're closer to someone, you feel a stronger gravitational pull. So it can't be any of these things. And you know what I should have originally said? Fg is, we're just using it as symbol F essentially, it looks like on there. Okay, so now we're left with two answers, 4F and 16F. We can figure out which one it is. So what we have here, so I'm going to basically plug it into this equation right here and compare it to what it was. So G is still the same. We still have M and M. R right there is now R over 4 squared. So let's think about what that is. So that's going to be G times M, R over 4 squared. We have to square each thing. So that's like R squared over 16. To me, it looks like it's changing by 16, so I'm going to think it's E, but let's prove it. So it's like 1 divided by 1 over 16. That's just going to be 16, which is essentially what that is. So we have like 16 times G M M over R squared. So it looks like it's 16 times bigger. And what I think about is this whole thing right here is just the same as this whole thing right there. And again, that whole thing right here we just called F. So for that whole thing that I highlighted in yellow, we can just plug in F. So this is like 16F. And that is our answer right there.